Bismillahirrahmanirrahim. We are interested in the floor of this quantity, which depends on the positive real numbers, alpha and beta. Alpha and beta are constrained to obey this inequality. Beta is superior to the cubic root of 2 over 3 alpha. The quantity we are interested in is alpha beta cubed plus the natural logarithm of 3 alpha beta squared multiplied by the integral x from beta to infinity e to the minus alpha x cubed dx. Since we are interested in the floor, this may give us a hint that what is needed is to have a bound on this quantity, a bound that is tight enough so that we know what this integer is. The integral itself can be represented using the incomplete gamma function. If we do the change of variables, y equal to alpha x cubed, x is equal to 1 over alpha to the 1/3 times y to the 1/3, dx is 1 over 3, alpha to the 1 over 3, y to the minus 2 over 3 dy. When x tends to infinity, y tends to infinity. When x is beta, y is alpha beta cubed. The integral can be written as y from alpha beta cubed to infinity, y to the minus 2 over 3, e to the minus y dy. We also have this outside factor, 1 over 3, the cubic root of alpha. The incomplete gamma function, gamma of a and z, is the integral t from z to infinity, e to the a minus 1, e to the minus t dt. If we make a comparison, the integral that we have is this factor, the incomplete gamma function with parameters 1/3, this power plus 1, and alpha beta cubed. When we bound the integral, we are basically obtaining a bound on this incomplete gamma function. In order to bound, we need an inequality. The inequality that is very helpful to us here is related to convex functions. If function g is strictly convex on the set big S, which is a subset of the set of real numbers, then for every x1 and x2 in S, x1 not equal to x2, we have this inequality. G of x1 is greater than g of x2 plus the first derivative of the function evaluated at x2. So of course, there is the assumption that the function is differentiable. The first derivative is multiplied by the difference x1 minus x2. We can check whether a function is strictly convex by examining the second derivative, assuming that the function is twice differentiable. If the second derivative is strictly positive on a set S, then the function is strictly convex on that set. Here we have two functions of interest. Both are strictly convex. X cubed, the first derivative is 3x squared, the second derivative is 6x, which is strictly positive when x is strictly greater than 0. E to the minus alpha x cubed, the first derivative, we get the exponential. By the chain rule, we have the derivative of this exponent minus 3 alpha x squared. If we differentiate again, we have to differentiate the exponential. We get it, and we get the square of this bracket here. Then we get the exponential multiplied by the derivative of this term, which is minus 6 alpha x. We can take the exponential and 3 alpha x as a common factor. We get this bracket, 3 alpha x cubed minus 2. The second derivative is strictly positive if this bracket is strictly positive. This requires that x is superior to the cubic root of 2 over 3 alpha. Note that this is exactly the mysterious quantity that appears in the problem statement. Note that beta is greater than this quantity, so over the domain of integration, the integrand here is strictly convex. This means that it is okay to employ this inequality whether we talk about x cubed or e to the minus alpha x cubed. Applying the inequality to x cubed, we will apply it to some x strictly greater than beta and beta. X cubed is greater than beta cubed plus the first derivative of the function, which is 3x squared evaluated at beta. So we have 3 beta squared. Then we have the difference x minus beta. Multiplying both sides by minus alpha, the inequality is reversed. We get minus alpha x cubed is strictly less than minus alpha beta cubed minus 3 alpha beta squared x minus beta. The exponential function is strictly increasing. We can apply it to both sides of the inequality to have an upper bound on the integrand that we have here. E to the minus alpha x cubed is strictly less than e to the minus alpha beta cubed minus 3 alpha beta squared x minus beta. We can integrate both sides from beta to infinity. This exponent here is minus alpha beta cubed plus 3 alpha beta cubed. This is e to the 2 alpha beta cubed. We need now to integrate e to the minus 3 alpha beta squared x from beta to infinity. We get 1 over this factor here multiplied by the exponential evaluated at beta. All in all, the upper bound is e to the minus alpha beta cubed divided by 3 alpha beta squared. Let's see whether we are heading in the right direction. In the problem statement, we need the floor of the logarithm of the integral multiplied by 3 alpha beta squared plus alpha beta cubed. Let's see what we have. The logarithmic function is strictly increasing. If we apply it to the inequality, we have log the integral less than minus alpha beta cubed minus log 3 alpha beta squared. If we move everything to the left-hand side, we can combine the logarithms. So we have log 3 alpha beta squared, then the integral, plus alpha beta cubed. And if we compare, it is exactly what we have here. Now we know something. From this bounding argument, this quantity is strictly less than 0. This means that the floor that we get will be a negative integer. This integer is -1 if we can show that this quantity is superior to -1. To upper bound the quantity of interest, we used the convexity inequality applied to x³. We got a lower bound on x³, and because x³ is multiplied by a negative number, which is minus alpha, then we get an upper bound on the integrand. To get a lower bound, we will apply this inequality to the exponential e to the minus alpha x³. Again, we take x that is greater than beta. x1 is set to x and x2 is set to beta. E to the minus alpha x³ is strictly greater than e to the minus alpha beta cubed. Then we have the first derivative of this function evaluated at beta, then the difference x minus beta. We can take the exponential as a common factor. We are left with a linear function of x. Specifically, we get 1 plus 3 alpha beta cubed minus 3 alpha beta squared x. Note that for a sufficiently large x, the lower bound is negative. The trick here is the following. We want to lower bound this integral. The integrand is strictly positive. We can lower bound the integral by restricting the domain of integration. We restrict the domain of integration so that the lower bound here is greater than or equal to 0. The lower bound is non-negative if this bracket is greater than or equal to 0. This implies that 1 plus 3 alpha beta cubed is greater than or equal to 3 alpha beta squared x. Divide both sides by this quantity. The lower bound is non-negative when x is less than or equal to 1 over 3 alpha beta squared plus this over that, this is beta. On the interval from beta to beta plus 1 over 3 alpha beta squared, this lower bound is non-negative. If x is greater than this threshold, then the lower bound becomes negative, and actually it tends to minus infinity as x tends to infinity. To lower bound our integral of interest, we first restrict the integral to that from beta to beta plus 1 over 3 alpha beta squared. This step is valid because the integrand is strictly positive in our case. Then we go back to our inequality here based on the convexity of the function e to the minus alpha x³ when x exceeds the cubic root of 2 over 3 alpha. We integrate both sides from beta to beta plus 1 over 3 alpha beta squared. We get a lower bound in this integral. The integrand is a linear function which can be easily integrated. The result of our integration is this constant times the length of the interval of integration. This is the exponential beta plus 1 over 3 alpha beta squared. We also have the exponential and this factor 3 alpha beta squared. When we integrate x, we get 1/2 x squared. We need to use the limits of integration. So here we get the difference beta plus 1 over 3 alpha beta squared whole squared minus beta squared. We get 2 over 3 alpha beta plus 1 over 9 alpha squared beta to the 4. We have the exponential. Take 1 over 6 as a common factor. We have 6 beta plus 2 over alpha beta squared minus 6. From here, we get beta minus 6. We have 3 over 9, that's 1/3 over 2, so 1 over 6. Alpha beta squared over alpha squared beta to the power 4. This goes away with that. We have 2 over alpha beta squared minus 1 over alpha beta squared. So this is 1 over alpha beta squared. The lower bound on the integral is e to the minus alpha beta cubed over 6 alpha beta squared. Let's recall the upper bound. The upper bound is exactly the same, but we have 1/3. Now we have 1 over 6. Here are both bounds. We can write down the lower bound as 1/2 e to the minus alpha beta cubed over 3 alpha beta squared. Apply the natural logarithm to all sides. We get the logarithm of the integral. Here and there, we get minus alpha beta cubed minus the logarithm of 3 alpha beta squared. Then we have minus log 2 in the lower bound. Now add alpha beta cubed plus log 3 alpha beta squared to all sides. We get that the logarithm of 3 alpha beta squared times the integral plus alpha beta cubed. This is upper bounded by 0 and is lower bounded by minus log 2. And this is very good news because log 2 is about 0.7, minus log 2 is about minus 0.7. This quantity here, which depends on alpha and beta, two positive real numbers with the constraint that beta is superior to the cubic root of 2 over 3 alpha. This function of alpha and beta is living in this narrow range between minus log 2 and 0. We don't know its exact value, but we are sure that the floor is exactly equal to minus 1.